Hello, welcome to the channel of Namagiri Academy. This is the next video in the series on multiple integration, and in this video we shall discuss the change of coordinates in case of triple integration. So before we do that, let's recall how we changed coordinates in the case of double integration. So suppose if we are given a real valued function f x y in two variables x and y, and if we are integrating it with respect to y first and then x, so this is basically double integration. So, and whatever are the um, limits of integration. So limits of the integration of f with respect to y will be in general the functions in x, and then with respect to x there will be some constants a and b. This is the general form of the double integral. Now if we want to change variables, then we defined two new variables u and v, and x is expressed in terms of new variables, and we call that function also as x, and y is also expressed in terms of the same two variables. And in order to integrate with respect to u and v, along with expressing this along with substituting for x in terms of u and v, we also multiply this whole this function f by something called as the Jacobian, and this Jacobian is defined as the determinant of del x del u del y del u del x del v del y del v, and then we can write this integral as f x u v. Now this x u v is an expression in u and v, because x is a function of u and v. Y u v Jacobian, this also is a function in u and v, this Jacobian, because each of these partial derivatives is a function in u and v. dv du, either dv du or du dv, depending on the order of integration, and these limits of integrations will change depending on what these functions are and how we are defining x and y in terms of u and v. So we shall have to calculate those limits of integration, so which I am not writing over here, but this is how we defined this was the change of variables in case of the functions of two variables. Now in case of the functions of three variables, we have something similar. So we have now to begin with a function f in three variables x, y and z, and we shall convert it into a function of three new variables u, v and w. So initially we are integrating a real valued function over the some certain limits, integrating limits, and we define now three new variables u, v and w. X is a function of u, v and w, y also is a function of u, v and w, and z also is a function of u, v and w. And these functions are something that we shall again denote by x, y and z. So now this Jacobian will correspondingly become now it will be a determinant of 3 by 3 matrix, del x, del u, del y, del u, del z, del u, del x, del v, del y, del v, del z, del v, del x, del w, del y, del w, del z, del w. And if this is the integral I, then we shall define I now as triple integral f x u v w. Now this x u v w is a function, is an expression in u v w, y u v w, z u v w, now we shall multiply this by this Jacobian x, y, z, d w, dv, du, and again the limits of the integrations, we shall have to change them accordingly as we have defined these three functions. So this is the change of variables formula in general in the case of triple integration. So in this lecture we shall see two specific types of change of coordinates, change of variables or change of coordinates. One is called as change into spherical coordinates, and the other is called as change into cylindrical coordinates. So in the case of double integration, we used polar coordinates. We saw how to change usual Cartesian coordinates into polar coordinates. We changed we expressed point x comma y as r comma theta, where r is the distance of the point x comma y from the origin, and theta is the angle that it makes with the positive x-axis. And so that is called as the polar coordinates. And now here there is something called as cylindrical, the spherical coordinates in the 3 dimensions. So in the same way as we can express point x comma y in the plane as r comma theta, we can express a point x comma y comma z in these 3-dimensional space using three different parameters which we shall call r comma theta comma phi. So now what are these r, phi and theta is something that we should try to understand first. Let us draw the axis, the Cartesian coordinate axis. This is the z axis. Generally we take this horizontal axis as x and this as y, but here just for the sake of convenience I am taking this as x and this as y. It doesn't matter, even if we choose this to be x and this as y, we can always make the necessary changes and make the same things work. Alright, so now suppose this is a point, let's say x comma y comma z, and we want to define three new parameters r, phi and theta, using which we should be able to locate the same point in the space. What are r comma phi comma theta? So first, r is the distance of this point from the origin, as in the case of two dimensions, as we had in the case of polar coordinates, r was the distance from the origin. Here this is the segment or the arm having length r. Alright, fine. Now what is theta? Theta, to define theta and also phi afterwards, let us first drop a perpendicular from this point onto the xy plane and connect the origin with the point. Let this be, let's say, P, and let this be Q. This point Q is the point of intersection of the perpendicular with the xy plane. Right? Now this, if this is the origin and if we call it as O, then let this OQ make the angle theta with the positive x-axis. Okay, so that this is theta that we have defined. Now what is phi? Phi is the angle that this segment OP makes with the positive z-axis. That is phi. So this is what we have defined, and these r, theta and phi, all three parameters together define this, or rather determine this point xyz completely in the plane. Let's see how. First also let's see what are the values of r, theta and phi, between which they vary. So each, let us discuss what are the possible values that each of these three parameters can take, the limits between which they vary. Okay, so first of all, r is the distance of a point from the origin, so it is certain that r is greater than or equal to 0, because distance can never be negative, and it is also clear that r can increase indefinitely, because the farther you go from the origin, the greater the value will be, the greater the value of r will be. So r is greater than or equal to 0, and it can increase indefinitely. So these are the limits of r. So r is not bounded above, it is only bounded below. Alright. Now what are the values of theta and phi? Okay, let us draw a new diagram. I will here to make to give you a better impression. This is z, this is x, and this is y. Now I am taking a particular case wherein this point P is lying in the YZ plane. P is in the YZ plane, and therefore when we drop a perpendicular from this point, is Q lies exactly on the y-axis, because we know that our point of intersection Q is in the xy plane. Okay, so it is in this plane, but since P is in the YZ plane, this Q will lie exactly on this y-axis. So this now theta is the angle that this OQ makes with the positive x-axis. So in this case theta is 90 degrees, or pi by 2 maybe. Alright, and this is phi. This is phi, which this OP is making with the positive z-axis. So now is this P the only point that is at a distance r from the origin, and that such that point Q makes angle pi by 2 with the positive x-axis? That is the question that we ask. Suppose we take another point, which suppose vary this point P in the circular fashion while keeping this distance from the origin unchanged. So we are actually suppose move this in the circular way and take our point P here. Okay, or maybe P prime, let's say P prime. Okay, we get a point in the YZ plane itself, and the perpendicular dropped from this point P prime. Alright, let it be Q prime, also will be lying on the positive y-axis, and therefore the angle that this Q prime makes with the positive x-axis also will be pi by 2. So this holds for all points if we do this for any point that lies at a distance r from the origin, and that lies in the YZ plane, the same is going to happen. Even for this point, let's say this will be suppose another point P double prime, you have Q double prime over here, even that will make angle pi by 2 with the positive x-axis. Even this point here will make angle. So whenever the projection from the point that is at a distance r from the origin and the point that lies in the yz plane, as long as the projection is on the y axis, the value of theta will remain pi by 2. So what are all such points? We want the point to lie in the yz plane and we want it to be at a distance r. So we actually get the set of all such points is in fact a semicircle this is also z axis but in the negative direction. This is the semicircle with radius r lying in the yz plane. Observe that again here also this for this point, if you drop a perpendicular from this point, it is on the y axis and therefore theta by definition is pi by 2. So for all these points the value of r is the distance from the origin to the point is r and theta is equal to pi over 2. So we are taking a specific so with this we get a semicircle over here, but what changes over here is the value of phi. We have defined the value of we have defined phi as the angle that this arm makes with the positive x-axis, and here we are changing this phi from 0 to pi when we are actually tracing this semicircle from this to this. The phi changes from 0 to pi. Alright, so now by keeping r fixed and pi also fixed over here, and by varying phi from 0 to pi, we get semicircle over here having radius r. Now think of rotating this semicircle, okay, in 360 degrees. So it's like completing one full revolution in this way. What would we get? We shall get a sphere, a hollow sphere of radius r. And what is happening when we rotate this semicircle? We are actually varying this theta from 0 to 2 pi. So keeping r fixed, varying phi from 0 to pi, and also if we vary theta from 0 to 2 pi, we get a hollow sphere of radius r. That means we get all points that lie at a distance r from the origin. Alright, so and suppose now this holds for every r. That means if we want to get a point at a distance r from the origin, then it, for some value of phi and some value of theta, we must find it somewhere, okay, for that fixed value of r. So therefore our limits between which r, theta and phi can vary are completely determined. R is greater than or equal to 0, 0 less than or equal to phi less than or equal to pi, and 0 less than or equal to theta less than or equal to 2 pi. They completely tell us. So these are the, this is the these new coordinates r, phi and theta, where these r, phi and theta vary between these limits, and we get any point in this space, three-dimensional space, can be expressed in terms of r, phi and theta, where they vary between these limits. Okay, fine. Now the question is, how are we going to express x, y and z in terms of r, phi and theta? For that, let us go back to this this diagram. Alright, see this P. So here we have P, X, Y, Z over here. Let us drop a perpendicular from P to Z axis. Let this be, say, T. Then this OT is the Z coordinate. But what is this OT in terms of phi? This OPT is the right angle triangle, and this cos of phi is OT divided by this hypotenuse of this right angle triangle is OP. Okay, so we'll write it afterwards. Cos of phi is adjacent side of phi, which is OT divided by OP, but OT is the Z coordinate of the point P, divided by OP is the length of this this is the length, okay, R, which is R. So Z is equal to R cos phi. Observe that we have succeeded in expressing Z in terms of R and phi. Similarly, we have to do for X and Y. Now here OT is R cos phi, then OQ is R sin phi. You can do it for yourself, check it for yourself, because this is phi, then this angle is pi by 2 minus phi, and if it is pi by 2 minus phi, then OQ is R cos pi by 2 minus phi, which means it is R sin phi. Alright, so OQ is R sin phi, and now we shall drop a perpendicular from Q onto the X axis and also onto the Y axis, in this way and in this way. This let this point be, say, S, we can call it any, you can give it any name. OS is the x coordinate of the point xyz. Alright, so therefore uh, and this OSQ also is the right angle triangle, and this is theta, this angle is theta, and therefore by trigonometry OS is OQ multiplied by OQ is the hypotenuse of this right angle triangle, so OQ cos theta. Observe that this OS, as I stated earlier, is the x coordinate, so x, this means x is equal to OQ is r sine phi cos theta. Alright, so again here observe that we succeeded in expressing x in terms of r, phi and theta, and y is OQ sine theta. Which is equal to r sine phi sine theta. So our job is done. So let us write once again x is equal to r sine phi cos theta, y is equal to r sine phi sine theta, and z is equal to r cos phi, where r is greater than or equal to 0, 0 less than or equal to phi less than or equal to pi, 0 less than or equal to theta less than or equal to 2 times pi. These are our coordinate. This is the spherical coordinate system. Any point in this space can be expressed in terms of r, phi, theta, and these are the conversion formula. Okay, now suppose if we want to so what is the Jacobian of this coordinate system? It is del x y z del r phi theta, that is del x over del r is sine phi cos theta, del y over del r is sine phi sine theta and cos phi, del x over del phi is r cos theta r cos phi cos theta, del y over del phi is r cos phi sin theta, and del z over del phi is negative r sin phi. del x over del theta over is equal to negative r sine phi sine theta r sine phi cos theta, and this will be 0. So when we compute this, this turns out to be r square sine phi. So I have checked this, you can check it for yourself. This turns out to be r square sine phi. Alright, so this is the Jacobian. Okay, good. So now let us solve one problem using change of coordinates into spherical coordinates. So suppose compute the volume of a sphere S having radius let's say A, centered at the origin. So the equation for this sphere is x square plus y square plus z square less than or equal to a square. We want to compute the volume, right? So we know that if we set our function to be uniformly equal to 1, and if we integrate over that region, then we get the volume of that region. So we shall integrate over this sphere with by taking 1 as the function in our usual coordinate system, and that should give us the volume V of that sphere. Okay, but by change of the coordinate system, by changing into spherical coordinates, V is equal to, now this is the function 1, so it remains as it is, multiplied by the Jacobian, which is r square sine phi, and now this dv is in fact actually here it is dz dy dx, but now in the new coordinate system it will become d phi d theta dr. Now since we are first integrating with respect to phi, now since we are considering the whole sphere, phi will vary between its whole range. Similarly, theta will vary between its whole range, 0 to 2 pi. And since we are taking the sphere of radius a, r is the distance of the point from the origin. So therefore these are all the points that are at a distance from 0 to a. Okay, so the collection of all such points. So therefore r will vary from 0 to a. That will cover the whole sphere. So whenever we are integrating over spherical regions, converting into spherical coordinates comes in very handy. In fact, that is why we make this change of coordinates. Here we are integrating with over a spherical region, and therefore we change into spherical coordinates. Alright. So finding out the volume is a specific case. Even if there is some other function over here instead of 1, it is, but we are trying to integrate over a spherical region, then it is always advisable to change into spherical coordinates. Okay, so now this is r square is constant with respect to phi. We are first integrating with respect to phi. So 0 to a, 0 to 2 pi, r square, integral of sine of phi is negative of cos phi, and limits of integration are 0 to phi d theta dr. Zero to a, 0 to 2 pi. This is negative r square cos phi from 0 to pi, meaning that we can change these limits and absorb this negative sign in this change of limits. So it will be like 0 to pi to 0. So r square pi of r square cos of 0 is 1. So r square 1 minus 1, so 1 plus 1 d theta dr. So this is 2 times r square. 2 times r square is a constant with respect to theta. So therefore it will be like 2 times r square theta 0 to 2 pi dr, which is equal to integral of 0 to a. It is 4 pi r square minus 0, and this is 4 pi r cube over 3 from 0 to a, which is 4 pi a cube over 3. So that is the volume of the sphere, and we know that the volume of sphere having radius a is 4 pi a cube over 3. So that matches with our prior knowledge. So that is how we, this is how we change the coordinates, and we get new coordinate system into spherical coordinate system. So that is one example of that. So I hope you understand spherical coordinates. So let us go over to the next part, that is the cylindrical coordinates. Cylindrical coordinates are quite similar to polar coordinates. In cylindrical coordinates, again we try to express a point x, y, z in using three new parameters, but one parameter remains unchanged, and that is z. So suppose we have a point here p x, y, z. Then we drop a perpendicular from P onto the xy axis. This is x, this is y, this is z, and we connect this let this be q. Connect this q with the origin O, and the angle made with the positive x-axis is called as theta. Alright, and let this OQ be R now rather than OP. This this is the z coordinate. Let it be as it is. Since this is OQ is R and this angle is theta, if we connect, if we drop a perpendicular from Q onto the x-axis and also onto the y-axis, we get the equations x equal to, and this, in that case, suppose if we call this point as S, then OS is OQ cos of theta, which means OS is the x coordinate, so x is R cos theta, and similarly y is equal to R sin theta. So this is very similar to coordinate axis and the polar coordinates in case of 2 dimensions, and z remains as it is. Alright, so we are getting a new coordinate system R theta z in place of x, y, z. Let's compute its Jacobian. So using our usual formula for the Jacobian, del x, y, z over del r theta z. This is the determinant of del x over del r. So let us write this cos theta del y over del r, which is sin theta, and del z over del r, which is 0 because z is not a function of r. Del x over del theta, which is negative r sin theta, del y over del theta, which is r cos theta, and del z over del theta, which is also 0 because again z also is not a function of theta, and now del x over del z, which is 0, del y over del z is 0 because both x and y are not functions of z. Here there is no term of z in the expressions for x and y, and del z over del z is 1. Okay, and this, if you simplify, if you compute and simplify, it is r cos square theta plus r sin square theta, which after simplification becomes just r. So that is the Jacobian here. So this is the Jacobian is much simpler than the Jacobian in case of spherical coordinates. Alright, so let us try to compute the in the similar way, try to compute the volume of a cylinder, which is, let's say, a cylinder having, this is x, y, this is z, um, cylinder having radius, let's say 2, and having height equal to 3, let's say, or maybe 4. So this radius is 2, so we have x square plus y square less than or equal to 2, and z varies between 0 and 4. Alright, so now since x square plus y, so since this is the disk having, sorry, this is 4 r square, okay. In the new coordinates r, theta and z is anyway as it is. In case of this cylinder, r will vary from 0 to 2, because r is the distance of the points from the origin to that point, okay, and the points in this cylinder, so this not the distance between the point and the origin. It is the, if we have a point in this space, and if we drop a perpendicular from the point to the xy plane, then the distance between the point of intersection of that perpendicular with the xy plane and the origin is r. This OQ is OQ, which is, this is r, and in this cylinder, if we drop a perpendicular, then it lies inside this disk of radius 2, and therefore r varies from 0 to 2. Theta is the angle that this arm makes with the positive x-axis, and since we are taking the whole disk, theta will vary from 0 to 2 pi, and z will vary from 0 to 4. And now since we are trying to compute the volume of this cylinder, let this cylinder be C, we shall integrate the function 1, okay, and that will give us the volume. So by changing into cylindrical coordinates, V is equal to R is varying from 0 to 2, theta is varying from 0 to 2 pi, and z is varying from 0 to 4, and this is the function 1 multiplied by the Jacobian, which is r dr d theta dz. Be careful about the order of the integration and the corresponding orders of limits of integration. Okay, r is varying from 0 to 2, so r square over 2 d theta dz this becomes 4 over 2, which is 2 d theta, and 2 this is 2 multiplied by d theta, but integral of d theta from 0 to 2 pi is theta, and after in substituting the limits, it becomes 2 pi minus 0, which is 2 pi. So this 2 multiplied by 2 pi, so I will not write this. Let us take a shortcut, directly write this as 2 multiplied by 2 pi multiplied by and dz. So this is 4 pi integral of dz, which is z zero to 4, which is 4, so 16 pi. So observe that the area of cylinder having radius r and height h is pi r square h. So here this height is 4 and the radius is 2, so therefore it should be, by our the formula that we know earlier, the volume should be pi 2 square multiplied by 4, so it is 16 pi. So that matches with our matches with the answer that we get using our high school level formula. Alright, so therefore I hope you understand this how we change our usual coordinates into cylindrical coordinates and how we integrate. So here again I would like to mention that we use cylindrical coordinates particularly when we are trying to integrate over regions that are cylindrical regions. That becomes very convenient. Again here we took a very simple example, which is that of constant function, but even if it were a function that was somewhat complicated, it wouldn't have mattered much. We would have simply changed into this into cylindrical coordinates, and accordingly we would have changed our function using these relations that x, y and z bear with r, theta and z, right? And by proper substitution we would have got a function here in r, theta and z, and we would have integrated that. The important thing is to properly use the relations between x, y, z and r, theta, z, and then properly determining the limits of integration. Alright, so that closes our discussion on the changing that is the change of coordinates in case of triple integration. So in the next lecture we shall study some other things. Probably there is something in the some part, the last topic in the unit of differentiation is still remaining, which is that of constraint optimization. So we shall discuss it possibly in the next lecture. Alright, thank you, bye.